This video will deal with sections 11.7, 8, and 9, and we continue characterizing the stars. In section 7, we're going to be using a diagram that was introduced by Astr and Russell to relate luminosity and spectral type. It turns out that by the time when these two astronomers were working on this field, they had a chance of obtaining the luminosity and the spectral type for many stars, and they realized that if you plot the luminosity and the spectral types of the stars that were known at the time by placing a dot for their corresponding coordinates for luminosity and for spectral type, curiously they found that many of the stars align themselves along this long snake here, but some go up here, some here, and there are a few down here. Well, this diagram is now famous and is known as the H&R diagram, and allows us to understand the evolution of stars during their lifetime. And this long sequence here is known as the main sequence. These turns out to be giant stars. These are supergiants, and down here are the white dwarfs. We can add more information. Turns out that the spectral type is related to the surface temperature, and the luminosity is related to the absolute brightness. Also, by looking at the sizes of all the stars when they are plotted, we see that this is our sun right there, and all the stars that would lie on this dashed line here would have the same radius as the sun, whereas any star that are on this other region are going to be larger, and the stars that are on this region are going to be smaller. And for instance, the giants can be 10 times as large, have a radius 10 times as large as the sun, or 100, and the supergiants can go all the way up to 1,000, whereas the white dwarfs are going to be 1/100th of the radius of the sun. So at the same time, we see that larger stars, the ones that are here, giants and supergiants, are going to have are going to be more intense in terms of luminosity, and the ones that are smaller than the sun are going to be less luminous than the sun, are going to be dimmer, and the sun, as mentioned before, is going to be kind of in the middle of it. So it's an intermediate star in terms of luminosity and temperature. It has to be noted that the temperature runs backwards, not in the usual way, but it goes from right to left. The temperature increases to the left. Again, we have the main sequence, and we see that there are different abundances of stars in different places of the main sequence. Again, the giants can be anywhere between 10 and 100 times larger in radius than the sun, and their temperature is also in this region between the 2,000 and 20,000, and the red giants are between 2,000 and 4,500. The supergiants can be up to 1,000 times larger than the radius of the sun, and the white dwarfs that turn out to be remnants of stars are about the size of the Earth and have very low luminosity. At this point, I ask you to open your lecture tutorial on page 117 and look at the H&R diagram. And please pause this video while you practice with your lecture tutorial. When you're done, you can come back and review your answers. In this lecture tutorial, we're going to look at the H&R diagram. We're going to relate the spectral type and the temperature and the absolute magnitude and the luminosity. Pre-activity question. The star A has a magnitude of negative 8.1. It's an absolute magnitude of 8.1, so it's going to be down here. Up here, negative 8.1. And it is known to belong to a spectral class B8. Spectral classes are down here, and we go from B0 all the way to B9 and then A0. So next to A0 is going to be B8, it's right there. So star A is here. Now star B has a magnitude of 11.2, which is way lower, 11.2, so it's going to be somewhere here. But it is also known that belongs to spectral class B8. So we go back to B8 and see that star B is going to be right here. So the question is, which star has the highest temperature, A or B? Well, it turns out that temperature is related to the spectral type. Since both of them are of a spectral type B8, both of them correspond to a temperature of around 1,000 or so, about 10,000 or so degrees Kelvin. So the answer is they have the same temperature. Getting into the lecture tutorial, we're given this diagram that shows different stars labeled like A, B, C, D, E, F, G. And then the question is, what are the spectral type, temperature, absolute magnitude number, and luminosity of star A? Well, star A is right here. The spectral type is going to be somewhere there. The temperature is going to be somewhere here. The absolute magnitude is going to be somewhere there. And the luminosity is going to be somewhere here. So the answers are there. The next question is, which of two pairs of labeled stars have the same temperature? Well, we have to check A, temperature. The temperature of A is this one here, and there are no other stars that have the same temperature. So A does not pair with any other star. B is here, and B, if we see, it has about the same temperature as C. So B and C can be said to have the same temperature. D and E also appear to have the same temperature. G, it's on its own. It's a little bit to the left of F, which is a little bit cooler. So the answer would be B and C and D and E. Question number 3. Do stars of the same temperature have the same spectral type? Well, these two guys have the same temperature, and if we move up, we see that they both fall in the same spectral type. The same as with D and E, they both fall in somewhere in the A something spectral type. So the answer is yes. B and C are of type, it says type B, but I would say it's type O something, like O7. And D and E are close to spectral type F. Question 4 says, which of the two pairs of labeled stars have the same luminosity? Well, we see that A could be said to have the same luminosity as G. B is a little bit higher in luminosity, not pairing with any other star. C probably has the same as F, and D does not pair with any other one, the same as E. So I would say A, G, and C, F. Question 5. Do stars with the same luminosity have the same absolute magnitude number? Well, we can check A and G. If we go to the absolute magnitude scale, which is this one here, we see that both of them correspond to somewhere around there, like 1 or 2, whereas C and D have the same absolute magnitude, somewhere around there, like 11 or so. So the answer is yes. Question 6. If two stars have the same absolute magnitude, do they have the same temperature? Well, we can see here that C and F, they have the same absolute magnitude, but F is extremely cold compared to C, which is much hotter, of the order of 20,000 Kelvin. So the answer is no. Number 7, stars of the same spectral type have the same. Well, same spectral type would have the same temperature. Number 8, the stars of the same absolute magnitude have the same. If they have the same absolute magnitude, they have the same luminosity. Question 9, for each of the following star descriptions, state whether the star would be a red giant, white dwarf, or main sequence star, and provide the letters of a star from the H&R diagram that fits the description. Well, for case A, we want something that is very bright and very hot, which translates into high luminosity and high temperature. So luminosity we want high, and temperature we want high, so it has to be on this upper corner here. I would say that is main sequence, and it would be probably a good case would be B. For case B, we want something that is dim and cool. So dim means lower luminosity, cool means lower temperature. So it's going to be something down here. So it's going to be main sequence again, and a good case is star F. Next is case C, in which we want something dim and hot. So dim is down here, but hot is here. So we're talking about white dwarfs, and a good case is star C. And finally, case D is bright and cool. Bright, cool meaning low temperature, so we're talking about red giants. Any of these will do, probably D or G. And this is the end of the activity of the lecture tutorial. We continue now with section 8. By looking at the difference in luminosity, it can be the stars can be classified into luminosity classes. We saw that the surface temperature is connected to the spectrum. We saw that classifying by spectral type is equivalent to classifying by the temperature. And this is the surface temperature, which is the temperature of the atmosphere. But stars of the same temperature can have different luminosities. And that comes naturally from here, because the same temperature would mean some stars that are along here, say, but one here is going to have low luminosity, and one of the same temperature can have a high luminosity. So these can be, the luminosity can be used to classify stars according to the so-called luminosity classes. The luminosity classes have been established somewhat arbitrarily, just by looking at the grouping of stars according to the luminosity here. So we have the 1A and the 1B, luminosity 1A, luminosity 1B, then luminosity 2, luminosity 3, luminosity 4, luminosity 5, and then down here, the white dwarfs. They don't have their own luminosity class. But we can see that the main sequence stars are going to be down here. The giants are going to be here, subgiants, giants, and then supergiants. They're going to go with different types of luminosities. Supergiants, they have luminosity classes 1A and 1B. The giants of different brightnesses can go between luminosity classes 2, 3, and 4. And the main sequence stars are going to be mostly luminosity class 5. So for instance, what can we say about a G2V star? Well, G2 refers to the spectral type, which is G. It goes from G0, G1, G2, so it's going to be somewhere here. We're talking about one of these stars. But since we're told that it's luminosity class 5, then it's going to be down here. It's going to be a main sequence star. We have G, we have V. So we're talking about G2V. We're talking about a main sequence star that has a temperature of about 5800 and a luminosity of about half, and an absolute magnitude of about +6. In section 9, we're going to see that knowing the spectral type and the luminosity class allows us to determine in an indirect way the distance of the star. And it is a series of steps. First, we need to observe the apparent magnitude and the spectrum. The spectrum will give you the spectral class, and with the spectral class, we're going to know the surface temperature. But the spectrum also tells you that whether we're dealing with a supergiant, giant, main sequence, and with this we can establish the luminosity class. So with that, we're going to have the luminosity class that will, along with the spectral class, will locate the object in the H&R diagram, and with that we can extract the absolute magnitude, which combined with the apparent magnitude will give us a way to determine the distance. One example, Regulus. We know that we're told that it's a B7b, which means that we come here, it's a B7 around here, and then it's a V, which means it's a main sequence, and this tells you that the apparent luminosity, we're told that the apparent luminosity as observed by an astronomer is 1.36. B7 is there. Class 5 means main sequence is there. So the absolute magnitude is -0.52. And now we know the apparent luminosity and the absolute luminosity, the absolute magnitude and the apparent magnitude. And with that, we can invert our relationship between the absolute and the apparent magnitudes to extract D out of this equation. So a little bit of algebra gives you the D is going to be equal to 10 raised to this power, little m minus capital M divided by 5 plus 1. In this case, little m is given as 1.36, is there. Capital M, we found that from the information that we were given, that the star was B7b, which means that the absolute magnitude is negative 0.52, so it goes there. So it's a minus with a minus gives you a plus. And all of this divided by 5 and added 1. So doing this operation with your calculator, we obtain the distance of Regulus to us is 23.33 parsecs. Okay, to continue, please go to the lecture tutorial on page 55. Luminosity, temperature, and size. Again, please pause this video and work the lecture tutorial entirely, and then come back to check your answers. Well, the goal of this lecture tutorial is to find a relationship between the temperature, the luminosity of the stars, and the size, the area of a star. And one question before we start: we have two stars, Antares and Mama. They have the same luminosity, but one, Antares, is cooler. So which of the two is larger? Well, luminosity is the power out, and power out means the energy being put out by the star. The fact that this one is cooler means that the radiation coming from here is going to have less energy. Each bit of radiation has less energy than the radiation coming from here. But if they have the same luminosity, they are putting out the same amount of energy, which means that this one is going to have to be putting out more pieces of light than this one. And because of that, it has to be larger. It has to have a larger surface. So the answer is Antares. Okay, part 1, luminosity, temperature, and size. We're given these 4 cases in which they represent heaters on the stove, and they vary by temperature and they vary by size. And the temperature is denoted here by the colors. So if we see something that is light gray, like in this case, it's going to have a high temperature. If we see something that is gray, a little bit darker, that is medium temperature. And if we see something that is dark, black, that means low temperature. And at the same time, we have small areas, medium areas, and small areas and large areas, and very small areas. So it's going to have 3 sizes: small, medium, and large. So in this case, question number 1, for each pair of hot plates, this is one pair, this is a second pair, third pair, fourth pair, circle the one that will cook a large pot of spaghetti more quickly. Between these two, which one would cook the spaghetti more quickly? Well, they are the same size, but this one is hotter. This one is cooler. It has low temperature. That means that it would be A. In this case, I'm jumping ahead. In this case, this one is not only hotter, but it's also larger. So it's going to be faster. In this case, we have the same temperature, but one burner is small and the other one is large. So in this case, it's going to be the large one. But in this case, we have one very small and one very large. But this one is medium, and this one is also, no, this one is high temperature. We can see that it's extremely light gray, like this one. And this one is medium temperature, like this one. So it's hard to tell between these two, because it could be that the size will overcome temperature, but we don't have the information. So there's a big question mark here. Question number 2. If you use 2 hot plates of the same size, can you assume that the hot plate that can cook a large pot of spaghetti is at a higher temperature? Well, yes, because if they are of the same size, the one that cooks faster is going to be the hotter one. Which of these cases would support the answer? Well, it would be A, this one here, in which we have the same size, but one is hotter than the other one. If we, in question 3, if we use 2 hot plates at the same temperature, can you assume that the hot plate that can cook the spaghetti first is larger? Well, yes, and it would be like this case. In this case, we have the same temperature here than here, but this is a small one, a small burner, and this is a large one. So this one would be cooking faster because it has a larger area. So it would be B. Now, if we use 2 hot plates of different sizes, can we assume that the hot plate that can cook is at a higher temperature? Well, in this case would be something like in this situation, in which we have a very small and a very large, but this one is very hot and this one is not so hot. Then it's hard to tell. In question number 4, I already got the answer. If we use 2 hot plates of different sizes, no, this is the answer of the previous one. We already answered that. But question 5, they are discussing the answer to question 4. 2 students. Student 1 says, in 1D, the hot plate of the left cooks the spaghetti quicker than the one on the right, because it's even though it's smaller. The hot plate is higher temperature is what makes what cooks the spaghetti more quickly. Well, the student 1 is wrong, because we cannot tell whether the temperature compensates for the size. The student 2 says the size of the hot plate also plays a role. If the hot plate on the left were the size of a penny, the spaghetti would take a long time to cook. I bet that the size difference, if the size difference were great enough, the one at the lower temperature would cook the spaghetti first. So the answer is that the student 2 is correct and student 1 is wrong. Question number 6. If 2 hot plates have the same temperature and one cooks the spaghetti more quickly, what can you conclude about the size of the hot plates? Well, what we can conclude is the one that cooks faster is going to be larger. Question 7. Likewise, if 2 stars have the same temperature, but one is more luminous, what can you conclude about the sizes of the stars? Well, the more luminous is going to be larger. Question 8. If 2 stars have the same temperature and are of the same size, which is more luminous? Well, in this case, they would be exactly the same in luminosity. Question 9. If 2 stars are of the same size, but one has a higher surface temperature, which star is more luminous? Well, it's going to be the one with the higher surface temperature. Part 2, applications of the H&R diagram. The graph here shows the the luminosity of these 5 stars versus the temperature. This is temperature, this is luminosity, and this is a representation of an H&R diagram. And question 10 asks star U and star B, they have the same temperature as we can see here. Given that star U is more luminous than star B, what can you conclude about the size of star U compared to the size of star B? Well, it's clear that U is going to be larger. In question 11, it says star U has a larger surface temperature than star X. We can see that U has a temperature that is way larger than X. Given that star X is actually as luminous as U, what can you conclude about the size of star X compared to the star U? Well, being equally luminous means that they are putting out the same amount of energy per unit time, same power. And since this one is putting out extremely energetic radiation, which is high temperature radiation, and this one is putting low temperature radiation, this one would have to put out way more light, way more radiation than this one in order to have the same luminosity. So this says that X has to be much larger. Question 12. Based on this information, which star is larger, X or Y? Explain your reasoning. Well, this is the same situation as U and V before, so X is larger than Y. Question 13. Which star is larger, Y or V? Y or V? Well, we see that they have the same luminosity, but this one is hotter than this one, so Y has to be way larger in order to have the same luminosity. Question 14. Draw a Z at the position of a star that is smaller than W, but with the same luminosity. So if it's the same luminosity, it has to be along this line, but we want it to be smaller. We see that if we put it here, it's going to be cooler, so consequently it has to be larger, so we have to put it here, so it's going to be somewhere there. It is difficult to predict how the size of star U up here will compare to the size of the star W. Explain what makes a comparison of these two stars so difficult. Well, the fact that this one is more luminous could be because it is hotter, but it also could be because it is larger. And the same for this one. So we have two variables acting at the same time, and we cannot tell which one is larger. They both have different luminosity and different temperature. And this is the end of this section.